Hello, my name is Austin Hamilton, and today I'll be talking about software complexity metrics. So in order to talk about software complexity metrics, we'll have to cover a few things first, and then we'll move on and talk about software complexity metrics and then wrap up. So first, I'll introduce you to the concept of software complexity. Then I'll move on to software complexity's history, how it evolved, how it started, where it is now. Then I'll move on to what software complexity metrics are, and then some popular software program complexity metrics, then a popular software systems complexity metric, and then finally we'll wrap up and give some final thoughts. So we'll start off by talking about what is software complexity. Well, software complexity is just a measure of how complex a software is. And what we mean by complex when we talk about software complexity is the measure of links and interactions within a software system. So the more functions and interactions between those functions and classes and interactions between those classes, and on a bigger scale, the more modules, so either microservices or embedded devices you have and how they interact in the overall architecture, that is software complexity. So a lot of times this is confused with complicated software. So a complicated system is just a large system with hard to understand code base, and that can mean it just has a lot of code. That can mean it's written poorly, but essentially, if you read it enough and look over it, you can understand it. A complex system is just a complicated system with lots of interacting and moving parts. So a complex system, while a complicated system can be understood given enough time, a complex system has many, many interacting parts, and so the amount of interactions you have to deal with grows exponentially with the amount of parts that are added to the system. That means that even with time, it is extremely difficult to completely understand a very complex system. Now, complex software is unavoidable in the real world. The bigger a system is, the more it does, the more is needed to make it run. The more complex it becomes, the more likely it is to get bugs, the harder it is to understand, and the harder it is to maintain. However, it's unavoidable in the real world as these systems grow. So now let's take a condensed look at the timeline of complex systems. So the first computer programs could easily be described as complicated. Now remember, a complicated program is one that, while it is hard to understand at first, given enough time and enough manpower, it can be understood. So the first programs were binary inputs, and they were usually just used to calculate simple functions and procedures. For example, the first successful stored program on the Manchester Baby calculated the largest factor of 2 to the power of 18. Now, the Manchester Baby was the first, or one of the first, computers that stored programs that were able to run on it. So, if you look at this program, it's a simple enough program, but the implementation of it can be complicated due to the fact that the inner workings of it were in binary. So, as programs evolved, software started becoming more complex. So compilers were built, languages from those compilers were built, and they were used to make more complicated programs. And then eventually, those complicated programs evolved into complex software systems. So now systems are made of, several programs, several APIs, several languages. They can be made from a multitude of different things that all have to communicate with each other. So there's a large amount of working parts, and the more parts you have, the more complex that becomes. So with these complex systems come several issues. So as software becomes more complex, it becomes more difficult to maintain. It also becomes easier for bugs to appear, and it becomes more difficult for new developers to create features for this code. So it became apparent that engineers needed a way to control this unneeded complexity within their software. So while software systems sometimes needed to be complex, getting rid of that unneeded complexity was extremely crucial. So in order to do this, they needed a way to measure the complexity of a system so that they could identify areas within the system. So let that be functions or objects, or as systems evolved, even individual programs. So they needed to identify these problem areas. Before about 1975, computer scientists and software engineers, they didn't have a good way to measure software complexity. The main metric for software complexity was lines of code. They just counted how many lines of code were in a function or a file or a system, and they used that as their measurement of how complex that system was. During the late 1960s and into the 70s, a push for research was made to look into software complexity. So around the time, I believe in 1976, 1977, two men named Maurice Halstead and Thomas McCabe independently created two software metrics to test the complexity of a program. So Halstead created Halstead metrics, and McCabe came up with something called cyclomatic complexity. Now it should be noted that these two metrics can only be used to really test the complexity of a single program. Later, it became apparent that these systems were becoming even more complex, and we needed a way to measure the complexity of entire systems as opposed to single programs. So a push was made to create metrics for entire systems. So that brings me to the first set of metrics, which are Halstead metrics. Now, when Halstead introduced his metrics, procedural programming was the major paradigm. So COBOL was a programming language that had taken major real estate within the software engineering field. Now, with that, Halstead developed metrics to measure the estimated amount of work or time it would take to understand or rewrite a code base. So Halstead, in order to do this, he had to define four important variables. Now, these variables are used later to create the so-called Halstead metrics. So these four variables are lowercase n1, which is the number of distinct operators. Distinct meaning, say you have one operator at one point in the code and the same operator in another point of the code. That's one in the addition of lowercase n1. So lowercase n2 is the distinct number of operands within a program. Capital N1 is the total number of operators within a program, and then capital M2 is the total number of operands in a program. So the definition that Halstead gives for operators and operands is not as concrete as many would wish to hope for. So things like keywords and arithmetic operators and even things such as brackets and semicolons, those are all considered operators. Now, to Halstead, operands are anything like variables and values for those variables. Halstead defines several metrics including program length, program vocabulary, program volume, program difficulty, and program effort. So the program length determines the total number of operators and operands within a program. The vocabulary is the total number of distinct operators and operands in a program. The program volume is a metric that is used to calculate approximately how much space a program will take up. Program difficulty is used to determine about how hard it would be to understand a given program. So you have the number of operators divided by 2, because most operators have 2 operands, multiplied by the total number of operands divided by the distinct operands. This gives an approximation about how difficult something will be. So the program effort is just the difficulty times the volume. Now the program effort is given a metric about how much time should be put into either understanding or rewriting a code base. So here is a simple example. Given the following C code, which just loops through all the numbers to 100 and prints out the even numbers, you have operators and operands. So the operators will be keywords such as int, printf, return, for, if, etc. They would also include any arithmetic operators such as plus plus and less than, and control operators such as the brackets, the parentheses, and the semicolons. So the operands would be the variables such as I and the values such as 0, 100, and 2. So, for example, one metric could be the program difficulty, and in this case, the difficulty would be the number of distinct operators, which is 12, divided by 2, times the number of operands in total divided by the total number of distinct operands. So that's 10 divided by 4, and this gives 15. Now, a second way of defining a program's complexity is through cyclomatic complexity. Thomas McCabe introduced this complexity measure in a paper in 1976. The idea is that the more possible paths a program can take at runtime, the more complex it is. And so to measure this, you look at the control flow graph and you count the number of nodes and edges in that graph and use the formula: the complexity equals the edges minus the nodes plus 2 times the connected components. For example, in the following control graph, you have 6 nodes. So you have start, D1, minus 10%, D2, minus 20%, and end. You have 7 edges connecting those nodes, and the number of connected components is 1. Now, connected components just means separate components, so there's only 1 here, and that's the whole thing, so we have 1. So the overall complexity is 7 minus 6 plus 2 times 1, which is 3. McCabe offered that any software program that has a complexity of 10 or above is a possible problem and should be handled. Now, moving on beyond software programs, we have to also measure the complexity of entire software systems. As software evolved, the focus has shifted from those programs and functions to architectures and modules. So you have, for example, microservices that interact with each other can be not as complex when taken individually. However, the whole system can be very complex when there are many microservices. So this whole system must be treated holistically to calculate the complexity of the software. Now, software system complexity metrics are usually coupling testings and things of that nature. So the idea is, for example, the more dependencies exist in a system, or the more API calls in a system, etc., the harder it's going to be to understand and maintain that system. So the most common way to determine the complexity of a system is through couplings. Couplings are the measurement of how modules communicate with each other, either across a program or across a system. So couplings can be hard to measure because they are entirely dependent on a programming paradigm and language. So, for example, the couplings in a C system are going to be different than the couplings in a Java or Scala system. There are several couplings to watch out for, which can be potential hazards. So common couplings are when modules access and change variables with larger scope, such as global variables. This means that they communicate through some global variable or at least some variable with a higher scope. External coupling is much the same way, except models are communicating through something like a file. Now, in object-oriented programming in particular, we have something called coupling between objects. So when two objects within an OOP system rely heavily on each other, this is coupling between objects. So, software has a long history with complexity. From the very first programs to modern systems, complexity has been highly coupled with programming. Complexity metrics were originally created to measure program complexity. So a single program could be measured to see how complex it was. But as software evolved, a need for metrics of an entire system became necessary. Now, software systems metrics can be used to locate potentially problematic code. Code that could be open to bugs, code that could be hard to maintain, things like this. However, these metrics are useless on their own. If we don't analyze these metrics and take in the software and the system and consider all of that holistically, we're just as blind as if we didn't use metrics in the first place. So, thank you. That is my talk on software complexity metrics.